There's the 3 feet. And the entire assembly is then moved forward 12 feet. So you're going to move this assembly from my right over here to my left by 12 feet. So you're moving the entire assembly 12 feet. All right. A constant force of 70 pounds is required to move the loaded hoist. So it takes me 70 pounds of force to move that 12 feet. Now here's the question. You've got to read this question very carefully. The total work input required to move the hoist is how much? What was the question? Did they ask me how much work was there involved in raising the weight or in moving the hoist? And the answer is how much work is there? The question is how much work is involved in moving the hoist? Let's take a look at the information they gave us again. We have 350 pounds. We raised it 3 feet. That has nothing to do with it. They did not ask you that question. They said, how much work is involved in moving the hoist? Well, that was 70 pounds of force, and you moved it 12 feet. So the total work to move the hoist is going to be, using our formula like this, it will be 12 times 70, or 70 times 12. And so the work involved in moving the hoist, and once again, make sure you read the question, is 840 foot-pounds. So now you and I know everything there is to know about work. What in Sam Hill is power? Well, power, and this is a great example of power. I tell you, we're talking about a lot of power, because look at this. We're moving this airplane up, but power is work per unit of time. We could take 10 days to lift this weight, or we could do it in a few seconds. And the faster we do it, the more power is required. Power is work for a unit of time. Power on the FAA written exam means rate of work and measured in terms of work accomplished per unit of time. So power is force times distance, that's work, divided by time. So the longer it takes to do something, the less power involved. Now the something you're doing, the force times distance, is the work. And if you spread the same amount of work over less time, it takes less power, over more time, I'm sorry. Spread the same amount of work over more time, it takes less power. Now, so how is a horsepower figured into this? Well, a horsepower is a unit of measurement. And 1 horsepower is equal to 33,000 foot-pounds of work accomplished in 1 minute. Well, the whole idea of a machine is that you accomplish an amount of work, but many times a physical machine, one that you're actually using your own energy involved with it, requires less power because you're using the machine, even though you're accomplishing the work. How does that do that? It spreads the same amount of work over more time. That's the whole idea of a machine. A good example of a machine is on figure 61 here in the FAA's booklet. And here's a pulley. And because you're using the pulley, you can accomplish the same amount of work moving this weight up, but because you use the pulley, you spread it over more time. And so it takes less power. That's the whole idea of a machine. Now you can figure out the advantage of a pulley, how much less force is required, by counting the number of strands of rope or cable that go back and forth. And you've got to be careful on this. The way this pulley is constructed is you have this attachment U here and this attachment U here. This is not a part of the attachment system going through here. That is the cable going up the back, or a rope going up the back. They make this drawing such that the ropes in the front are light colored, the ropes in the back are dark colored. If you count the strands here, there are 1, 2, that's the dark one, 3 is the light one, and 4 is the dark one. 4 strands. So the mechanical advantage is 1 to 4, and therefore it takes 1/4 of the force that otherwise would to operate this pulley. Now if you have a hard time seeing that, we have redrawn it to make it easier for you. And here we are again, the same thing, and here are the 4 strands, 1, 2, 3, 4, like so. And so the mechanical advantage is that you have only 1/4 of the force involved. So if you wanted to lift this weight of 60 pounds, how many pounds of force would it require? And the answer is 1/4 of the force, or 60 pounds divided by 4, or 15 pounds. And that's a question they're going to ask you on a test. Now an inclined plane does exactly the same thing. An inclined plane is a real simple machine, and it takes the same amount of work but spreads it over more time and therefore requires less power. It's a simple machine that on the FAA written exam facilitates the raising or lowering of heavy objects by applying a small force over a longer distance and therefore a longer period of time. So they have a question on the test that says you're going to take 120 pounds and raise it 3 feet by rolling it up a 9-foot ramp. How much force will be required? Well, it's going to require a ratio of 3 to 1 or 9 to 3 or 3 to 1. So let's take a look at the formula for it. So all you have to do is force on a ramp, the force required is the ratio of the height to the length. And the height is 3, the length is 9, and you'll multiply that times the weight, and that tells you the force applied. So let's take a look at the actual numbers in this particular case. And the numbers are, you have a 120-pound barrel, 9 feet plane, 3 feet height, and as it works out in the formula, as we do this, it'll be 120 pounds times 3 divided by 9. It's a ratio of 3 to 9, or 40 pounds. And you use your electronic calculator. So you can see that it takes 1/3 the force to move that barrel up because this ratio is 1 to 3. Now, as you can see, machines can provide a tremendous amount of mechanical advantage, and another system that provides a mechanical advantage is a hydraulic system. And the way a hydraulic system works is like this. You have fluid come in, and it presses down on the piston and shoves the piston down like so. Now, a hydraulic system is governed by Pascal's law. Now, I have never met Pascal. In fact, I know nothing about him except that he has a law. And so let's take a look at Pascal's law. It says the force available in a hydraulic system is equal to the pressure in the cylinder multiplied by the cross-sectional area of the piston. So you take the area of the piston and multiply it times the pressure, and that's the force applied on the cylinder. So you can make a formula out of it. You can say that force equals pressure times area, and you can abbreviate it a little bit by saying F equals P times A. Now, let's take a look at a couple of questions they're going to ask you, and let's take a look at the first one here. They're going to say you have a piston with an area of 1.2 square inches, and it has 850 pounds of pressure. What is the pressure put out by this piston? And the answer is force equals pressure times area, so it's 850 psi times the 1.2. You just use your calculator to multiply that out, and you get 1,020 pounds. Now, that's very easy, so let's take a look at a little bit more complicated one. This time, they tell you you have a double actuating cylinder and has a 3,000-pound pressure in the system. And double acting means that the piston inside the cylinder is powered in both directions. You can have fluid come in from this direction and push this piston in this direction, or you can have fluid come in from here and push the piston back in the other direction. And they tell you the piston has a surface area of 3 square inches on this side, which is the extension side, and it has a rod with a cross section of 1 square inch on the retraction side, which would be this other side here. And what they want to know now is how much force this actuator will be able to produce when you're retracting. Well, let's go back to our formula. Force equals pressure times area, and the pressure is 3,000 psi. Aha, but be careful. What is the area? Well, the piston has 3 square inches total, but there's a 1 square inch rod. So what's the area pushing on this piston upward? And the answer is 3 minus the 1, or 2 square inches. So now you have 3,000 times 2 for a force of 6,000 pounds. Now watch out. You can be sure that if they ask you a question like this, they will give you an answer choice that gives you the force times the whole area instead of just the area minus the rod. So be careful. Make sure you get the area right here. And now that wraps up what the FAA wants you to know about physics.
Let's talk now about fluid lines and fittings. And let's start off talking about flexible lines. These are our flexible lines for carrying different types of fluids. Now, flexible hose can be used in aircraft fluid systems, but only according to the manufacturer's specifications. So you've got to make sure where flexible hose is allowed to be used on different aircraft. Now, the material used in the inner liner of a flexible hose determines its suitability for different fluids. And you'll generally find 4 different kinds of materials used in the inner liners of flexible hoses. Those materials are Teflon, butyl, Buna-N, and neoprene. Now, Teflon is compatible with nearly every liquid used in aircraft, including petroleum products. Butyl, Buna-N, and neoprene are different synthetic rubber compounds. Buna-N and neoprene can be used for petroleum products, although Buna-N is more desirable. Although butyl is not suitable for petroleum products, it is suitable for phosphate ester-base hydraulic fluids such as Skydrol. And Teflon is also suitable for phosphate ester-base hydraulic fluid. So what if you were asked which among these 4 hose materials, Teflon, butyl, Buna-N, or neoprene, are compatible with phosphate ester-base hydraulic fluid? Well, now you know that you could use a hose with either a Teflon or a butyl lining. Now, flexible hose, as opposed to metal tubing, is classified according to the inside diameter of the hose. So, what does this mean if you have a system that has both metal tubing and flexible hose? Well, if you compare a 3/8 inch high-pressure aircraft flexible hose with 3/8 inch metal tubing, you can expect them to have equivalent flow characteristics. And that's because even though the inside diameter of the flexible hose is the same as the outside diameter of the metal tubing, the inside diameters of both are close enough in size to not significantly affect the flow characteristics. Now, it's common for an aircraft fluid system to have both types of lines. Rigid metal tubing is used when it can be attached to non-moving structural portions of the aircraft. However, flexible hoses have to be used in lines that connect a component that moves or vibrates relative to the aircraft structure. That's a situation that would break a rigid metal tube. Flexible hoses are also used where a line has to be repeatedly connected and disconnected. So flexible hoses and metal tubing rarely have interchangeable applications. By the way, since a 3/8 inch flexible hose has a 3/8 inch inside diameter, its thick wall construction causes it to have a much larger outside diameter, or OD, than a 3/8 inch metal tube that has a 3/8 inch outside diameter. So remember, if you're comparing a 3/8 inch aircraft high-pressure flexible hose with 3/8 inch metal tubing, the important thing to remember is they will have equivalent flow characteristics. Now, some fluid lines carry fluid which may be physically dangerous to people if it gets loose and gets on the people. A fluid line that is carrying that should be marked with the letters PHDAN for physically dangerous to people. Now, because the plumbing lines may be fairly long on large aircraft, they'll identify them at regular intervals with color-coded bands and with geometric symbols unique to each type of fluid system, and that helps avoid confusion. The FAA wants you to know that although the colors of the colored portion of these bands will vary depending on what kind of system it is, the geometric symbols, and these geometric symbols change depending on the kind of system, the geometric symbols are always black on a white background regardless of the contents of the line. Now, flexible hose has a linear stripe on it, which is also called a ley line. The purpose of it is to reflect hose twist, and hose twist is a bad thing. When you install flexible hose, it should not be twisted. A bend, some slack is fine, but it should not be twisted because that's going to reduce the strength of the hose, and the purpose of having that linear stripe on there is to tell you very clearly whether you have indeed accidentally twisted the hose as you're installing it. Now, as I said, you must have a certain amount of slack in flexible hose when you're installing it, and the reason for that is when it's under pressure, it's going to do two things. It's going to contract in length, and it's also going to expand in diameter when it gets under pressure, and that's why it needs the slack in order to be able to contract in length. Okay, how much slack does it have to have? Flexible lines have to have 5 to 8% slack. They have to have 5 to 8% slack. Alrighty, given that, the FA will say to you, we want to know if you have two fittings that are 50 inches apart, what the minimum hose length is that you're going to need to make that connection. And that's based on the minimum amount of slack that you have to have. And how much slack did I say you have to have? 5 to 8% slack. Okay, let's take a look at how those numbers work out. The distance between the connectors is 50 inches. The minimum amount of slack is 5%. 5% times 50 inches gives you 2.5 inches. So 2.5 inches is the additional length the hose needs to have to allow for the minimum amount of slack. And 50 inches plus 2.5 inches for the slack gives you a minimum hose length of 52.5 inches to make that connection with the minimum slack that you have to have in the flexible hose. Now, a term that is associated with flexible hose is the term cold flow. Cold flow is what you get with the deep permanent impressions that you have in a flexible hose, and those permanent impressions are produced by the pressure of hose clamps or supports, and that deep indentation is called cold flow, and it is associated with rubber hose. It is not associated with metal tubing. Now let's talk about metal tubing. In a metal tubing installation, you do not want the tubing to run straight. You want to have a bend in it because tension in it is not desirable. Tension in metal tubing is undesirable because pressurization, when it gets the pressure of the fluid in it, will make it expand and shift, and that will create problems if it's under tension. Now, when you have fluid or pneumatic metal tubing in an aircraft, what you do not want to do is have short stretches of straight tubing. The aircraft is going to expand and contract due to temperature changes, and there is no practical way to avoid that. You just cannot avoid significant temperature changes in an aircraft. So the way that you want to avoid stress on the tubing from those temperature changes is to make sure that you've got bends in it. The best way to avoid excessive stress on metal tubing due to that expansion and contraction is to provide suitable bends in the tubing. So when you're fabricating and fitting rigid fluid lines, you'll have to make bends in those lines. And as you can imagine, bending a thin wall tube requires proper technique to get the desired result of maintaining a smooth inside surface and original diameter. Kinks, wrinkles, and excessive flattening, reducing the tube diameter, are not acceptable. When you make a bend in a tube, the flattening of the bend cannot be more than 25% of the original diameter of the tube. So flattening by not more than 25% of the original tube diameter is permissible. Now, in addition to bending tubing, you'll most likely have to cut it. When you're cutting a metal tube, it's important to make sure that it ends up with a square end. And the best tool for cutting moderately soft metal tubing, such as that made of aluminum, is a hand-operated wheel-type tubing cutter. Although you can use a fine-tooth tack saw, it's more difficult to get a clean square end with a hacksaw. So the best tool to use when cutting aluminum or any moderately soft metal tubing is a hand-operated wheel-type tubing cutter. Now let's assume that you've got scratches or nicks in an aluminum alloy tubing. Scratches or nicks can be repaired by burnishing the tubing unless it's particularly bad. And how is bad is particularly bad? Well, if the scratch or nick is not in the heel of a bend, then you can repair it by burnishing, or if it's in a straight section, it can be no deeper than 10% of the wall thickness. So if you've got a scratch or nick in the straight section, it can be no deeper than 10% of the wall thickness, or if it's in the heel of a bend, which means the outside part of a bend, you can't have any scratches or nicks there. Now, let's assume that you're going to be supporting metal tubing. When you're installing metal tubing, you want to use bonded clamps, and when you put on those bonded clamps, you want to remove the paint or anodizing from the tube at the clamp location. The purpose of using bonded clamps, particularly with fuel lines, but also hydraulic and oil lines, the idea is to bond it to the structure so that you don't have any problems. And when you do that, you need to remove the paint or the anodizing from the tube at the clamp location. So for metal tubing that's carrying fluids, you want to be using bonded clamps. Unbonded clamps are the kind of clamps you use for support if you're installing wiring as opposed to fluid lines. Now, when you're working with metal tubing fluid lines, how are they sized? Well, they're sized by wall thickness and also by outside diameter, not inside diameter, but outside diameter. And the size increments that are used are increments of 1/16 of an inch. Now, with tubing, to find the inside diameter of tubing, what you need to do is to subtract 2 wall thicknesses from the outside diameter. Metal tubing, as opposed to flexible tubing, is measured according to the outside diameter, and then you've got the wall thickness, and if you want to know the inside diameter, what you have to do is subtract 2 wall thicknesses from the outside diameter. And here is an example that the FAA might give you. They'll say to you that you're going to make a replacement oil line, and it is 3/4 inch 0.072 aluminum tubing, and it's 5052-0 aluminum alloy tubing. And the question is, what is the inside diameter of that tubing? Well, 3/4 inch tubing is the outside diameter. The 0.072 is the wall thickness. And remember, we said that you're going to use the, take 2 times the wall thickness and subtract it to get the inside diameter. Okay, the outside diameter, 3/4 inch, is 0.750 inches. 3/4 of an inch, 0.750. The wall thickness is 0.072, and what you need to do is subtract 2 times the wall thickness. So 2 times 0.072 is going to give you 2 times the wall thickness, a total of 0.144. Now, the outside diameter in decimals instead of fractions is 0.750. The 2 times the wall thickness total comes up to 0.144. 0.750 minus 0.144 gives you an inside diameter of 0.606, an inside diameter of 0.606. So the first number they gave you, the 3/4 inch, was the outside diameter, and the second number, the 0.072, was the thickness of the wall, but you need twice that thickness subtracted from the outside diameter in order to get the inside diameter. Now let's talk about flares and flare fittings. And AN, or Army-Navy flare fittings, have pretty much replaced the AC or Air Corps fittings in newer aircraft. The fittings, the AN versus the AC fittings, have different shapes. Sometimes they're interchangeable, but not always. So if the FAA says to you on the test, are AN and AC flare fittings totally interchangeable? The answer is no. Sometimes they are, but not always. Now, how do you identify AN flare fittings as opposed to AC fittings? Well, on the AN flare fittings, there is a shoulder between the threads and the flare cone, and that shoulder is what allows you to identify an AN flare fitting as opposed to an AC fitting. The AC fitting does not have the shoulder. Now, if you've got an AN flared tube fitting designed to go on steel tubing, if you have a steel fitting, the color of it is black. They are color coded, and for steel flared tubing fittings, the color code is black. If you're flaring aluminum tubing for use with the AN coupling nuts, the angle that you're looking for on that flare is 37 degrees. You're looking for a 37-degree angle, exactly that angle, and that is different than they use for automobile connectors. And it's designed that way specifically to be different than automobiles so that you don't get them mixed up between the two. Don't use automobile connectors when you should be using aircraft ones. Okay, what you use is a two-piece tube connector consisting of a sleeve right here and the nut. And that's what you use when you're making a tubing flare, because what that type of connector does is eliminates the possibility of reducing the flare thickness by wiping or ironing when you're tightening it down. The use of the sleeve and the connector keeps that flare intact when you're tightening it down. Now let's suppose you over-tighten this coupling nut. Where would damage or weakness to the tube be likely to happen? If you look at this exploded view, you can see that damage to the tube would not be to the entire tube. It would be at the junction of the flare and the sleeve. So over-tightening a coupling nut could damage or weaken the tube at the sleeve and flare junction. Now, the FAA is going to ask you what is the correct sequence of steps that you're going to make when you make a single flare on a piece of aluminum tubing. They're going to give you all of the steps, and then they're going to ask you to put them into the correct order. So here's the correct order that the FAA is looking for. And if you've done it some different way, that may work in practicality, but this is the order the FAA wants you to give them on the written exam. First thing you're going to do is you're going to slip the fitting nut and the sleeve onto the aluminum tube that you're going to flare. Here's the sleeve and the fitting nut. You've put that on the tube. The second thing you're going to do is place the tube in the proper size hole, whichever is the proper size for that size tubing, in the flaring box. The third thing that you're going to do is center the plunger or flaring pin over the tube. So you've centered the plunger or flaring pin over the tube. The fourth thing that you do is project the end of the tube slightly from the top of the flaring tool. And how far out do you project it? About the thickness of a dime. The fifth thing you do is tighten the clamp bar securely to prevent any slippage. And the sixth thing you do is you strike the plunger several times with a lightweight hammer or mallet and turn the plunger a half turn after each blow. And those are the 6 steps in order that the FAA wants you to be able to tell them on how to make a flare. And this is what it's going to look like when you get all done. Now, sometimes you will make, instead of a single flare like this is, you will make a double flare. And the advantage of a double flare is it's more resistant to the shearing effect of torque. Now, couplings come in various sizes. And how do you tell the coupling sizes? Well, the FAA says that there's going to be a dash and a number after the end of the coupling. Maybe they used to be. These days, a lot of times it doesn't have any dash number, but the FAA is still going to ask you about it. The in dash number on an 8-1-8 coupling, there would be a dash and then a number, 2, 4, 8, whatever it might be, 12, indicates in 1/16 of an inch increments the size of the tubing on which that particular nut should be used. For instance, they will say what size coupling nut should you use with 1/2 inch aluminum oil lines. Okay, a 1/2 inch is how many 1/16ths? A 1/2 inch is 8/16, and 8/16 means that the coupling nut you would use would be an 818-8, 8 for the 8/16, which is the same as a 1/2 inch, and that's the size of coupling nut that you would use on a 1/2 inch aluminum line. Now, there are also fittings that you're going to be working with that are military standard or MS flareless fittings. And the MS or flareless fittings are not tightened with torque. They are tightened by turning the nut a specified amount after the sleeve and fitting sealing surface have made contact. And MS flareless fittings are not torqued to tighten them down. Instead, they are tightened a certain number of rotations, a certain amount of turns or partial turns after the sleeve and the sealing surface have made contact. Now, let's talk about hydraulic lines and what kind of lines you can use. The kinds of lines that are going to work as far as hydraulic are concerned if you've got a high pressure system is corrosion resistant steel